Sorry? Functions in this, in the whole function relation thing.
Sort of. What specifically one-to-one answer functions and how functions
Okay.
well, if anyone wants to add anything to that.
If you have lecture notes to go with that, I'll have a quick look at them.
Probability or discrete.
Functions and relations and sort of one-to-one and onto and that sort of thing. What are we looking at? That's cool. No, that's all right. Okay, so what you've done in that's in the discrete bit, right, isn't it? So what you've done here is you've got a really, really, really general concept of function. Okay, so you're used to in maths thinking of a function as a machine that takes inputs in and spits outputs out. Okay, that's what in math, in most maths, you're used to it being like that, and you put your x into the machine, and it does whatever it does, and it spits out a y. You're used to thinking of functions that way. You're also used to thinking of functions as a graph. You're also used to thinking of functions as something like that. Okay? So firstly, let's fix that. It is okay to think of functions in both of these ways. Okay? But the most general definition of function is actually a relationship between all the possible x's and all the possible y's. You're saying that in this setting, I'm saying that this number y is related to this number x because they create a point that is on this line. Okay? So the rule for knowing whether the number x and the number y are related is, can I create the x from the y? Okay, so there's this third picture of, or there is a set of x's and y's such that x and y are related by y equals f of x. Okay? In Maths for IT, this here is the definition of what a function is. Okay, so you only create this formula from knowing about which points on the diagram are related to each other. So what you actually do is that you can get this picture and you can draw and colour in all the points that are related to each other. You can say, it's related, according to this rule, colour in those points and, oh my goodness, that's the graph of y equals f of x. Wow! Okay, that's the concept behind it. You're so used to thinking of functions in the other direction because that's how you've been taught. But when Descartes first came up with coordinate geometry, he was thinking in the other way. He was saying, I want points, an x and a y coordinate that give me a point on the plane, and I'm going to collect some of them that have some property, and I want to try and find a formula that describes that shape that I have drawn. You've for so long been taught about maths from the direction of I have a formula, what shape is it? But this coordinate geometry was really originally about I have a shape, what formula is it? Okay? And that deep connection between formula and shape is what calculus is about. And this is the real theoretical underpinnings of what it even means. And not just for real numbers, but for anything. Okay? Right. So, this is a useful picture. You can colour in, you can have one object and something else, x's and y's, and you can colour in all of the pairs x, y that are related according to your relation, and if, as a graph, it looks like a function, then it is. And a function satisfies the vertical line test. A vertical line crosses the graph of a function once, if at all. It doesn't have to cross it at all. But, okay? So, right. So, but we have to go back and think about what a relation is. So a relation is that you get numbers or objects or anything at all, and you say that any two of them, you can decide whether they are related or not by some concept of relatedness. Okay? So relatedness is defined to be a set of points such that x and y are related when, and insert rule here. Okay? That's a relation. Okay, and you define it as a set. And the set of all possible x's and y's is known as S. So the x's are from S and the y's are from the set T. Okay? Right, that's relations. And so we can draw a picture of a relation. Okay, it's just a relation is a set of things, and every possible pair you can decide by some sort of rule whether they are related to each other or not related to each other. Okay? So you might have, for example, ABC 1, 2, 3. This could be my S here. And these are my T. Okay? And the relation will be, you colour in some points in this diagram, and that is the things that are related. So just as an example, you might have my relation is the set of x, y in ST such that, give me a second, x has y strokes, where S is A, B and C, and y is 1, 2 and 3. Okay? So the rule for deciding whether they're related is that the letter X, when drawn, has y strokes of the pencil. So A takes 3 strokes to draw, 1, 2, 3, it's related. B takes 1, 2, 3 strokes to draw, it's related, so B is related to 3, and C takes 1 stroke to draw. Those 3 stars is my relation. This is a function because it satisfies the vertical line test. It's not a one-to-one function because it doesn't satisfy the horizontal line test. But you can't say it that way in maths for IT. A function is a relation such that everything in S has exactly one thing in T that it's related to. Okay, A is only related to this thing in T, B is only related to this thing, C is only related to this thing. And they're all related to something. There is a point involving A that is in the relation that involves T, it's something in T. Everything's got something, but everything is related to something else, okay, in T, and only one thing, okay? That's one version. One version of the relation is that you get a rule which tells you when they're related or not, okay? But sometimes you can just say, the rule for when they're related is if it's in the diagram. And so you just say, I declare that the things that are related are these things, and you just list them. Okay? I could have said that the relation is just A3, A, B3, and C1. And that would have been a perfectly good way of describing the relation. Okay? So I could have started there. So the concept of coordinate geometry is that you start with a list of all the things that are related and you look at it and go, you know what? That's the number of strokes that it takes to write those letters. Awesome, now I have a rule. Okay? So there's this concept here where you can go e.g. r equals set of xy such as xy is coloured in the graph below. This is supposed to be a circle, by the way. Okay, and there it is. They're the ones that are coloured in. Just that circle itself. Okay, that's a relation. That's not a function because it doesn't satisfy the vertical line test. Okay, so if this was a function of everything from R to R, firstly, not everything has a point above it or below it. But it's also not a function because some of the points have two things that they're, some of the x's have two y's that they are related to. So, but I can also rewrite this relation as that. And so now instead of having it has to be in the graph, I have it satisfies an equation. Okay, so this is really a list, and this is a, cool, I don't need a graph, I can just plug in the numbers and tell if it's in the set. Okay? Right. And so you talk about, does she, he, she, who's teaching this? Oh, sorry? It was Naomi. Does Naomi talk about the X, R, Y, like related to? Yeah. And so back here we can say that A is related to 3, B is related to 3, and C is related to 1. Yeah. Yep.
So are A, B, and C elements of S?
Yes.
And 1, 2, 3
Elements of T.
Why do you have Y equals 1, 2, 3?
Oh, sorry, thank you.
I was just confused.
Yeah. Thank you. T is the set. Y is in 1, 2, 3. Sorry about that. Yes, I can't, yeah. T is a set. So I could have written Y is in 1, 2, 3 if I wanted. Thank you. So that's the big idea for relations. And so what you have is that some relations are equivalence relations, some relations are functions, and some functions are one-to-one. So every relation has an inverse relation that works the opposite way around, where you pitch the first coordinate as the second coordinate, and the inverse relation, you just flip your drawing. So the inverse relation of this original one would have the ABC here and the 1, 2, 3 here. They don't have to be in order, it just makes it easier to do it. So, and the 1, 2, 3 here, and so it will be the other way around. And that wouldn't be a function because firstly, not everything has a, if I'm going from these to these, not everything has something, 2 doesn't have anything to be related to. So yes, and an equivalence relation is generally not a function. An equivalence relation, everything has to be related to itself, so you know that the diagonal has to be filled in. But I mean, this isn't an equivalence relation because equivalence relations have to be with one set and the same set again. So it would have to be ABC here as well for it to be an equivalence relation. All right, so I don't know if that's enough talking. Feel free to keep asking anything you have to say about that particular thing because I haven't covered everything, but that's the big picture that's in my head when I think about those things. And so what you can do is you can turn most relations that are functions, you can turn it into that the rule is that y equals something in terms of x. For all functions, it's possible to find y equals something. Well, the big philosophy of maths is that it's possible to find y equals something, no matter how complicated it is. It might be too hard to do that, but you can at least say y equals the matching y coordinate of the point above x on this thing here. So you can pitch it that way if you want to. So our traditional version of function matches with the relation version of function as either this or as this. Yeah, where x is in wherever x comes from. So you're saying, yep, I'm going to do all the x's, and the y-coordinate that goes with them in the point in my picture of the relation is whatever y-coordinate comes out of my function, which is what this bit here is saying. And so now that gives you a list, and you can, if you want to, you can draw a table that describes all of the y's that go with all of the x's. So a sequence, which we do in equivalence relations, is a function from the integers to anywhere. And so you say, well, A0 is just f of 0. And so you can draw a sequence as a relation as well. You just have 1, 2, 3, 4, 5, whatever on the bottom, and then whatever their actual values are on the y-axis, and just put the dots in. Yeah. Okay, so there is a definition of one-to-oneness, and I've run out of paper. I have one more. Did Naomi tell you the formal word for one-to-one? Obviously not. It's called injective. That's what they call it over in economics, because they like to use fancy words. Onto is surjective. Sur meaning on in French. So one-to-one means that for every... Well, let's have a look at the actual definition. We say that a function is one-to-one whenever f of s equals f of t implies that s equals t. Okay, so you've got this definition, and this works for functions. And so you've got your relations, and then what you've done is you've said, all right, for every x, I've got an x, y is in my picture, I'm going to call the y that goes with this x, f of x. That's how you do it. So back here, you go, cool, I'm going to, every point in this graph, I'm going to call the y that goes with this x, I'm going to call it f of x. And then I've got a formula for how that works. Okay? And now I can start thinking of it as input-output. So a one-to-one function is if f of s equals f of t, then s equals t. So note that's an if-then statement. To prove that something is one-to-one, you have to say, suppose f of s equals f of t, working, therefore s equals t. Okay? And to prove that something's not one-to-one, you just have to show that if s isn't equal to t, that there are s's and t's that aren't equal that produce the same function value. Okay? So, alternatively, there's another version, or if s is not equal to t, then f of s is not equal to f of t. Either one will do. They are both definitions of one-to-one, because this is the contrapositive of this. Okay? So, what this is telling us, to prove that something's one-to-one, you'll have to go, suppose and do some working and then go therefore s equals t. That's proving that a function is one-to-one. To prove that something's not one-to-one, that's okay. You just need to find an s and a t with s not equal to t, but f of s is equal to f of t. And that they're particular s's and t's. These ones are general s's and t's. This is algebra. And these ones have particular numbers or objects, okay? Okay, so this one you have to do a proof. This one you just need a counterexample, okay? You just need one pair of numbers that are different numbers but still come out to have the same function value. And that's proving that things aren't one-to-one, okay? So as an example, all right. N factorial, all right, as a function, okay, so f of n equals n factorial, yeah, on n including 0. That's an n. All right. F of 0 is 0 factorial, which is 1. F of 1 is 1 factorial, which is 1. So not one-to-one. Okay, that's proving that things aren't one-to-one. Proving that things are one-to-one is a different story entirely. Oh, can't put a square bracket there. So that's the interval from 0 to infinity, by the way, in case you haven't done Maths 1A, because not everyone in Maths for IT has. Okay, so prove that f is one-to-one, and that's what we're going to do. So first we need to say, suppose f of s equals f of t for s and t in the domain of my function. Okay? And then I get that s squared equals t squared, because that's what f of s and f of t actually are. Alright. So either s plus t equals 0, or s minus t equals 0, and this one would mean that s is equal to t. That's cool, that's where we wanted to end. We wanted to end at s equals t, because that's what the proof is supposed to do, so that's good. So we either need to show that this tells me that s is equal to t, or that this is impossible. Okay? So, well, we know that s and t are both positive, and the only way to add two positive numbers together to get 0 is for them both to be 0. Because they're both positive, right? So, s and t both positive, so therefore s equals 0 and t equals 0, so again s equals t. So, s equals t in either case. So I have a proof that began with suppose f of s equals f of t, and finishes with so s equals t, therefore it's one-to-one. Sometimes you have to split it into cases like that, but yeah. That's a good trick. It's always worth knowing in any math course that if you get two definitely positive, like non-negative numbers and add them together to get 0. The only way to do that is for both of them to be 0, because you can't add two positive numbers and get 0, because it would be bigger than 0. So both non-negative. And that's proving that things are one-to-one. Yep. It wouldn't have been one-to-one. And I could have, if the domain had been, let's just do it, e.g. f of x equals x squared on the whole of R, then you could go f of 1 equals 1, f of minus 1 equals 1, so not one-to-one. And that would be enough. So they're quite different, right? Proving that things aren't one-to-one is really easy if they actually are one-to-one, if they actually aren't. Onto means that everything in the space that it's going to is covered. So, yeah. It should. Using this proof method, you'll get to a stage at some point where you'll go, oh, well, if this happened, then S wouldn't be equal to T. And you could go back and go, cool, that's going to help me think of something where it's definitely not equal. Like where the S and the T aren't equal, but they still came out to the right answer. So if you had done this with the x squared, like coming down here, the only point where we used the fact that S and T were positive was here, and we could have gone, well, that would mean that S equals minus T. Cool, so that's telling me that if I choose S to be 1 and T to be minus 1, we'll get the same answer. Yeah, and so I can put it back in the original and go, actually, I get the same result now. Yeah. So you could have said S equals minus T, you say, well, that's not possible because S is positive and that would make T negative and T can't be negative. So, yeah. Okay, onto. The definition of onto is for every T in the outcome, because it always goes from S to T, right? There is an S in the input space with f of S equals T. So all that means is that every possible T is covered by at least one S. There's allowed to be more than one S that get to that point, but every possible T is covered. So my original relation, which was a function that I drew, isn't onto because it doesn't cover 2. There is no ABC that produces the answer 2, and so it's not onto. So proving that something's not onto is actually quite hard because you actually have to find out what all the answers are and go, there isn't one here. Okay? So you just need to find, one T in the outcome space that isn't covered, and that will make it not onto. Otherwise you have to show that every possible T is covered by something. Yes, and sometimes you do wave your hands a bit. So x squared, if you use as your outcome space the whole of R with x squared, it's not onto because you can't get minus 1. If you use as your outcome space just 0 to infinity, it is onto because you can make any positive number as a square of something. But if you use as your outcome space n, so there's all these different options for what might happen. I was sure I had yet another page where I used it. If you use as your outcome space n, then it's not onto anymore. If you're thinking of x squared going from n to n, it's not onto anymore because not every natural number is the square of a natural number, and so. e.g. f of x equals x squared, with f sending n to n, like that. So that's my s and that's my t. It's not onto because 2 is not equal to f of x for any x in n, right? There is no natural number that will square to give 2, okay? Yeah, whereas from R to R, you have that that actually isn't onto either. Not onto because -1 is not equal to x squared for any x in R, but f of x equals x squared for f going from R to 0 to infinity is onto as for any y in 0 to infinity, there is an R, an x that subs. We have that f of root y equals root y squared equals y. Okay, so there is a number x that I can pick, and the x is called root y, that produces the answer I was thinking of. There's actually 2 numbers that do that, but that's okay, you only need 1. It'll still be 1-to-1, it'll still be onto even if there's multiple answers that give this, multiple x's that give the same y. To be both 1-to-1 and onto, everything has an outcome. All outcomes are covered, and they're only covered once. Yeah. Well, that's probably as far as I can go, because you can probably talk to Naomi herself about it from now on.